So this is another step 2 question, 2011 question number 2. It's question 1 from the Miscellaneous Pure step 2 support module booklet thing. Write down the cubes of the integers 1 to 10. So we're going to write them down and we're going to leave them there for the duration because step doesn't ask you to do that kind of thing just for fun. Somehow that's going to be helpful to us later. But in any case, we've written them down. Positive integers, super important throughout this question that we're just working with integers. X, Y, and Z satisfy this relationship here. In the case x plus y equals k, show this thing here. Now, a very useful result to memorize here. X cubed plus y cubed, a sum of cubes, and indeed a difference of cubes, can both be factorized. If you replace x with minus y, you'd get minus y cubed plus y cubed equals 0, of course, which means if x equals minus y is a solution to this, that means x plus y is a factor, right? So therefore, we can factorize an x plus y. We need an x squared here and a y squared there to make that work. And then we're not looking for any of the middle terms. Right now, we've got a plus x squared y, so we're going to need a minus x squared y coming from somewhere here. And from those two, from this one here. So maybe a minus xy to make it go away there. And this will work. You can just memorize that result. And likewise, there's a similar one for x cubed minus y cubed, which you should also know. Anyway, if we have that, then we can replace that bit there with that and equal kx cubed. But of course, if x plus y equals k, that's the whole point of this. Those two things cancel out. And we can also replace, because notice here it doesn't have any y's, replace y with x minus k. Sorry, k minus x, of course. So cancel out this with this, because they're the same. And they're also not 0, since they're positive integers. And replace the y with this. And then it pretty much very quickly gets down to this, which is what they wanted us to get. Perfect. So we've got that, and we've done this, and deduce this is a perfect square. So why don't we just take this that we've just found here and just create this out of it? So let's just times everything by 4, and then let's take away k squared, which just takes 1 away from there. Then let's just divide the whole thing by 3. And then just notice that this is indeed a perfect square. It's k minus 2x all squared. And because these are integers, this makes the squared thing an integer as well. And so that is indeed a perfect square. And also show that z cubed is stuck between these two things. So what we could do, I guess, is we could firstly start up here and just say, well, from here, if you factorize out, the 3x from these two bits here, k minus x is a positive number because if x and y are both positive integers, k is bigger than x. So this is a positive number, and x is a positive number. So we're removing something from k squared, removing something positive from k squared. So therefore, if we just don't remove it, this side is bigger, and we get z cubed, therefore, is less than than k squared. So that's very easy. That's this bit done. Now, what about the other bit? Well, okay, let's look at this section now. And what we can do is we can just say that this is obviously bigger than 0 because it's something squared. So therefore, obviously, this is bigger or equal to 0. We can times over by 3, and then we can add k squared and divide by 4. And we'll end up with z cubed is definitely bigger than that business, which is the other side. And so we're done with both sides there. Use these results to find the solution of this equation when k is 20. So when k is 20, we can just substitute k as 20 into all of the things that we've done so far. So into this, into that. We can also put it into this, remember, was the formula I had at the bottom of the page previously. I can put k as 20 into that, makes it look like that. I can also put k as 20 into this stuff over here. And yeah, now this is where these numbers come in, right? Because if you know z as an integer that's stuck between, that when cubed is stuck between 100 and 400, that leaves it to be either 5, 6, or 7. So that's why we wrote these out, just to remind ourselves that actually we don't have a lot of cases to check here. And often when you're dealing with integers, it's just a case of checking the limited number of cases you can actually have. So looking at this here, if we just substitute in z is 5, we can just do the maths. It doesn't end up being too terrible, all this. This is clearly not an integer, so this is not going to work at all. So it's not 5. Then we can substitute in 6, maybe, and check. That one does also not make an integer. 8, 14, no, okay. So no, not that one either. And then when you put in 7, of course, you could just probably hope that it works at this point. But it does indeed. It makes 324 if you divide that. And 324 is, it's what, 18 cubed? Sorry, 18 squared, is it? So 18 must be this, which means x is 1. And of course, if x is 1, y from here is 19. And that will be our solution. x1, y19, z7. Good. Next bit, by considering a different case here, x plus y equals z squared. So we're essentially gone all the way back up to the top of the question, but they're giving us z squared instead of k. And now we have to do the whole thing again, all the way through. maybe without as many short stops in between. We just have to do it all ourselves. Except we have all these results, and actually, all of these results that we worked out will still hold, just replacing k with z squared. Like k was just any number, right? Any integer, and z squared is an integer. So if these results hold, these two in particular, for x plus y equals k, they'll hold for x plus y equals z squared, as long as we just replace z squared in for every k on here. So, okay, well, firstly, of course, this is the original thing we're looking at, x cubed plus y cubed equals kz cubed, but k is 19. So that's just that bit there. But these two results here, what I'm saying is they hold with z squared replacing the k. So of course, if you replace z squared k with a z squared, you're replacing k squared with z to the 4 and z to the 4 again. And now we can divide everything here by z to the 3 because z isn't 0. And because they're all positive integers from the very start. And so z is less than or equal to 4. So that massively narrows down anything that we're going to have to check. And also we can, of course, refactorize this sum of cubes, which is exciting. And an x plus y is z squared, so we can put that in. And then we can divide by z squared, and we'll get this. And now, okay, so you've probably, with z less than or equal to 4, you could just try stuff now, I think. Like, that's probably limited enough to just try stuff. You could just use this as 16, and you could just try cases. I don't think it's the best idea. I think there's something intelligent you can do here, which is, I mean, it almost factorizes, doesn't it? It's like a square thing. And if you kind of just invent a 2xy here, only to take them away later, it does absolutely just factorize, which is kind of it. And why, like, where are we going with that? Like, why is that helpful? I almost gave it away by accidentally clicking the button there. But the reason this is helpful, of course, is because x plus y, that's z squared, right? So I've forced another x plus y in there, just like on this very first line. I forced an xy in there, x plus y in there, just like on the very first thing we did when we cancelled the k much earlier. I just forced another one in there. That's why I was doing it. So I can replace that with z, I can replace that with z squared, which makes that z to the 4. And now I can say, well, z to the 4 is bigger than 19z because this is positive, right? So z to the 4 must be bigger than 19z, which means that z cubed is bigger than 19, which sticks. I mean, well, okay, so z is now just 4. Is that right? Or 3 as well, sorry, 3 cubed. I was thinking 3 cubed was 8 for a second because I'm an idiot. But z is 3 or 4, right? And this, of course, is where our two cases are going to come from. Again, you probably could have just tested all the z's 1, 2, 3, and 4, but this is quite a nice way to enable you to only have to look at these two. So yeah, cool. So right, we've got z is 3 or z is 4, and now if we put in z is 3, we'll get from here x plus y equals. Well, okay, I'm putting it in the first one first. Actually, sorry, I'm putting it in there first. But I'm also getting, and actually, yeah. So you don't even have to use this one anymore, do you? Because you can just say, this is why these cubes are so helpful. What two cubes add to make 513? Well, those two work quite well, so I can just take those two. So we get that solution. And if z is 4, we can put this in. And again, it's not too hard to spot these two, is it? 10 and 6. And so we'll get that solution as well. And those are our two pairs. Thank you for watching, and I will see you next time.